All right, so we might as well get started. Hi, everybody. Welcome. My name is Alex Schramm. I am currently the chair of physics, and we wanted to have this get together so that you could get to know us, we could get to know you. We realized that first-year students have probably never even seen our building and our facilities, and in general, what we do. Apologies in advance for the lack of pizza. Usually we do have pizza and drink, but alas, that's not happening. We'll owe you double next year. How's that? In any event, so the plan is to, each of us will have a few minutes to say something, talk about various aspects of the program. And at the end, we'll pause for whatever questions or whatever that you may have, okay? So we're going to start with Professor Eggleston, who's going to give us a tour of Hameetman Science Center. Dennis?
All right. Well, hello, everyone. I'm Dennis Eggleston, professor of physics here. And my job is to give you a brief tour of our home Hameetman Science Center. So let me switch the camera around. Okay, so here's the entrance to the building. I was going to start outside, but the Wi-Fi is a little weak out there. As you come in, right to your right here is the physics common room. So this is a room that we have built for students to use and study in. It's a little bit of a mess right now, so I'm not going to actually go in here. Off to the left is our Foucault pendulum. So as you can see, it swings back and forth like any old pendulum. But the interesting thing about this is that the plane of the swing slowly rotates. And this is a demonstration of the fact that the Earth is rotating. So you learn all about that up in upper division physics. Okay, coming down the hall here. On this hall, we have our staff and faculty offices. So first office here is where Elise, our departmental assistant, works. See some of your favorite professors along here, Professor Umansky, Professor Scheel. I don't know who this guy is, but he zooms in once in a while. No, sorry, Alan. Professor Gavreau and Professor Starwalt. Let's not forget our lab assistant, Chuck. Couldn't do without him. And then here's me, and finally, Dan Snowden. Okay, so the hall rotates around here. Now we're going to take a right and go down to where our intro labs are. So the intro labs are here on the right side of the hall. There are 3 of them corresponding to our intro classes. Let's just take a quick peek inside. This one, ooh, dark in here. Okay, so this is one of our intro labs. We have some experiments set up right now. This is one that we're currently doing in Physics 230. Over to the side here, we have an experiment to measure the charge to mass ratio of the electron. So again, all the labs kind of look like this. Each station has a computer. We set up various experiments. You can see we have a full array of supplies here for our lab work. So you'll visit these labs when you're doing your intro courses. Okay, so now I want to take a quick jaunt downstairs. On the lower level of Hameetman is where our more advanced lab courses are, as well as our research labs. So there are many of those. My time is short. So today I'm just going to show you my research lab and give you a brief introduction to that. Okay, so here we are on the lower level. And here is the plasma physics laboratory. Now, first thing to note is that plasmas have nothing to do with blood. When we talk about plasmas, we're talking about ionized gases. And most of us don't have much experience with plasmas because at atmospheric conditions, plasmas cool and become normal gases. But they're quite ubiquitous in outer space. The sun and interstellar space is filled with plasmas. Probably the most common experience we have with plasmas is in fluorescent lights. So here on the top of my toolbox, I have a fluorescent light, and for half of it, this half over here, the white coating on the inside of the glass tube has been scratched off. So when I turned it on, you can see that on the left-hand side, it looks white like a normal fluorescent light bulb. But on the right-hand side, you can actually see what's inside. So that glowing blue gas is a plasma. Now, when I release the on-off switch, you can see that it almost instantly goes away. And so this is a problem if you want to study plasmas because they don't hang around very long. So that's where my work comes in. What I do is I try to make a bottle to hold on to the plasma. And you do this using electric and magnetic fields. So this apparatus here was built by my students and myself over the years, and it is a plasma confinement device. So we shoot a plasma inside and then study it in a controlled manner. Over on this side is the controls for all of that. You can see it's fairly complex. Okay, well, that's all I have time for. But if you're interested in plasmas and you'd like to know more about them, I'd be happy to Zoom with you about that. So I think now it's Janet's turn.
Hello, can everybody hear me okay? Okay, great. So I'm going to briefly talk about my research too. Hang on one second while I try to share screens. And let me know if you can see this. You should see a black window with command lines on it. And I'm just going to briefly bring up a movie so you all see this movie. Yes, hopefully. And what it is, can somebody say yes? Do you see the movie or not? No? Oh, no. Okay. All right. Well, so much for that. For some reason, that does not work. I've never tried that before. Okay. Well, can you see anything at this point? I must apologize.
We see you. The share is gone.
Yeah, I don't know what happened. Oh, well, that's life.
You're muted now. Janet, you're muted right now.
Yeah, I think you hit the space bar and muted yourself.
Is it working now at all? Can you hear me?
Yeah.
Okay, sorry about that, guys. I can't show movies from my computer with Zoom very well. I apologize. I was going to show you some movies about my research. I study turbulence in fluids. But if you're interested, come by, Zoom with me at some point. But what I was really wanting to tell you about is just how to get involved in research in general, because I think it's really important for students to do. I think it's a great opportunity for undergraduates because we have such, I don't know if you've heard about our summer research program, but you can basically do research, get paid to do research over the summer. It's one of the best opportunities. If you're interested in doing and sometimes you can also do research during the year as well. It depends on the professor. But if you're interested in doing research in physics, we have a physics festival usually in January. So definitely stop by for that. And keep an eye out for that, I should say. Also, just you could go to our website and see what each of us is doing. And if you're interested in what we're doing, just contact us. We'd be happy to talk to you, tell you about our research. No strings attached. We're just going to talk about it. We love to talk about it. That's about all I had to say. And sorry about I don't know what's going on with my sharing, but oh well.
Janet, you can post it on a website and tell everybody where it is.
Okay, okay, sounds good.
Yeah, I would just add real fast, the physics festival that we'll probably do at the end of January is an opportunity for all the professors to talk about what kind of work they're doing, how many students they're looking for and what they can do. And that's the time that we really roll up our sleeves and try to plan for the summer research program. But as Professor Shield says, if you have interests now, there's nothing to keep you from talking to professors and finding out what they're doing. The purpose of the festival is to have a one-time presentation so everybody can see at once what's going on. Okay, Professor Stierwalt, please.
Hi, can everyone hear me? Yes? Okay, I'm Professor Stierwalt. I am an extragalactic astrophysicist. So that means the kind of physics I do is astrophysics. And in particular, I look at galaxies outside of our own Milky Way. So our galaxy, the Milky Way, has something like 200 billion stars in it, like our sun. So our sun's super special to us, but actually a little below average. But there are 200 billion suns in our galaxy alone, and then there are hundreds of billions of galaxies outside of our galaxy. And so I study what happens in particular when two of those galaxies smash into each other. And I'm very interested in the star formation. So when two galaxies smash into each other, you get lots of star formation because stars form out of collapsing clouds of gas. Hopefully you can see this image. So I wasn't ballsy enough to do a movie, so there you go. Image works. Here you see two galaxies that haven't completely merged together, but they're sort of feeling the gravitational pull of each other. And so the white, hazy, gray, blue is showing you where the older stars are. And then the pink and the purple knots are showing you where new stars are being formed, potentially because they're feeling the presence of the other galaxy. So I'm stop share. I'm going to share something else. So I look at this from many different angles, but one way I do this is I get data from the Hubble Space Telescope. And so here is the crew I had over the summer. Here's our website is in the top left, but I'm still populating it, so it's a little sparse right now. But we had a virtual research crew this summer, so these are our virtual selves. And we did, so everyone was looking at Hubble data, and now many of these students are going to be going to conferences over the semester and next semester and presenting some of the work. So super excited about that. And before I end my piece, I wanted to ask, this question is for the students. Chuck, no, nothing from Chuck. Can you tell me what big astronomy news we had this week? Anyone?
Go ahead, whoever was.
I think some scientists find on Venus some chemical substance that indicates that life could exist.
Yes. Okay, Sylvia. If you send me my email is Sabrina@Oxy, it's my first name, Sabrina. If you send me your mailing address today, this is a giveaway. I'm gonna send you a Google Cardboard headset. So we sent these out to all of the students in Physics 162, which is astronomy. And it is a VR, virtual reality headset that you put around your phone. And then you can load virtual reality videos and then watch them. Super awesome. So I will send one to you. It comes like this before it's opened. If you send me your address, okay?
Thank you.
Yay! So yes, we found a molecule on Venus called phosphine. I say we, astronomers, I didn't do it. And that got played out in the press as a sign of life. Well, potential sign of life. Thank you, Alec. More about the headsets. So potential sign of life, maybe. Could it be aliens? Maybe. Is it aliens? Probably not. But phosphine here on Earth, it's actually a very toxic chemical. We use it as a fumigant, but it's also produced by bacteria. So on Venus, surface temperatures are super hot because the greenhouse effect has gone off the rails there. So Venus is actually hotter than Mercury, even though Mercury is much closer to the sun, because of this thick blanket of greenhouse gases. And so even though it's super hot at the surface, we don't know very much about the surface because it melts everything that we try to send there to learn more. But if you go up far enough, about 50 kilometers up from the surface, you start to get temperatures that are Earth-like. And so astronomers have always wondered, could there be some form of life in those clouds? Not life like us, we're talking about microbial life. And so this phosphine, they can't explain it any non-biological way. Does that mean it has to be biological? No, but they haven't been able to explain it any other way. So still super exciting. That's it. That's what I got.
Okay, my space bar stopped working. That was terrific, Sabrina, thank you. Okay, so now we're going to hear from a couple of students who did research for professors in the department. We're going to start with Gabe Gregory, please.
Hey folks, my name's Gabe. I'm a senior. I've been a physics major here at Oxy for a while now. It's kind of crazy. And I got involved in research the summer after my sophomore year. I've been working with Dr. Snow-Nift on some of his dark matter type stuff. And the school let me come into the lab this summer and let me do this research, and I've been allowed to continue it through the academic year. So I've been pretty stoked. So I thought I'd just kind of show you guys a little bit about what I've done. I'm down here in the basement of Hameetman in Professor Snow-Nift's lab. And this is what I've been able to build this past summer. Basically, my research is trying to shine some high energy light off of this copper plate right here. And then I can control the voltages around this computer board I made. And actually in the center of this computer board, there's like a 10 micron hole, which is about it's a hundredth of a millimeter. And then there you go. Show you what's inside that. So this is what I've been building. Can't really see it that well, but let me put it right here. Yeah, so basically I have here a super strong magnet that I'm trying to use to bend these charged particles that I'm interested in, and I'm going to try to determine their mass. So the school has funded me, and they've helped me purchase all this stuff, and it's been a lot of fun, a lot of freedom, and it's a pretty dope thing to get involved in is research in the physics department, because we do it pretty good. So I know the professors have been mentioning the physics festival that's coming up at the start of next semester. So that's a lot of fun to get to see what these professors are working on. And it's just a blast to get down in the lab. So that's what I've been up to.
Terrific. Thank you very much, Gabe. And now we'll hear from Caroline Fuller.
Hi, I'm Caroline. I'm also a senior in the physics department. I did research this past summer also with Professor Snow-Nift. He's kind of got two specialties. His first is dark matter and his second is renewable energy. So I've been working with him on renewable energy stuff, which I think is really exciting because it's kind of more of a, it's not as much theoretical physics. It's a little more maybe even engineering focused, but we were looking at solar panels specifically. So we partnered with Southern California Edison over the summer, which is the big power company down here. And they gave us a bunch of data. I guess I can show you one of my slides. So these are just, I basically spent the summer doing a lot of coding, running through a lot of energy and power data. And we made these curves, which are tracking solar production during any point in time during the day. So we have these for a bunch of years. So we spent a lot of the summer just working on the algorithms. And then we ended up with this kind of plot, which is showing how much the solar capacity grew in this region over 6 years. So it was just super fun to work with Professor Snowdenift over the summer. Definitely grateful that this was something that we could do virtually. So, you know, not as exciting as Gabe to be in the lab, but it's still definitely a possibility to do virtual physics research. So that's really exciting. Yeah, I guess that's all I have to say about that.
Terrific. Thank you, Caroline. And speaking of Dan's lab and renewable, Dan, take it away.
Okay, hello everyone. I'm not in the lab. I'm actually standing up on the back of the campus here, the east end of the campus, about halfway up what's called Mount Fiji. And I thought it would be fun for me just to show off the college's solar array. So let me see if I can flip the camera around here. Okay, so there's very smoky LA out in the distance there. And then all around me is the Occidental 1 megawatt solar array. So the solar array was installed after a long and hard 4-year fight to get this thing built. As you see, it's kind of got this odd shape to it. I guess it's more evident if you look over here. There's nothing regular about it. Turned out that art was a key to getting the solar array accepted. And so it has a very neat looking artistic figure, which is completely not evident when you're standing here on the hill. And by the way, I'm not supposed to be standing here. So if you see the police cars coming, then I will have to make post haste off the hill here. Okay, so the solar array cost us $7 million to install. We got a half off rebate from the city of Los Angeles, so $3.5 million to install the solar array, which we basically took out of the college's endowment. That was what the big fight was about. Since then, the array has produced 12% of our electrical energy. Right now, it's probably near max, or it would be at max if there wasn't so much smoke in the air. And we're probably producing about 50% of the college's power right now. But of course, we get none in the middle of the night, and it goes down substantially in the winter. Okay. The solar array saves us about $300,000 every year, and that number is increasing rapidly. And the prediction was that we would pay off the solar array in 12 years, which is how we sold the board on expending the money to do this. Right now it's at about 15 years, but the LADWP is being very helpful in jacking up the rates like crazy. So I think we're probably gonna meet that 12-year mark at the end of the day. Okay, so since I'm up here and I don't usually come up here and students are not supposed to come up here, I thought I'd just show you a little bit of stuff about what this thing, little sort of view of the under the hood, as you will, for the solar array. So so the panels are in these tables, these sort of rectangles, and you see the solar panels on top of them. We'll come back to those, but each table is mounted on 3 pylons, and you see one there at the end, one in the middle, and then one down here at the end. So these pylons are kind of incredible. Below them, it's not really clear now because the dirt has kind of covered them up, but below each one of these pylons is a 1-foot concrete pillar that goes all the way down into bedrock. And so that could be up to 20 feet on some places of the hill. The other remarkable thing is, check this out. This is not a nice install. Look at that. Each one of these tables is at a very slightly different angle, okay? And so there was a surveyor who I actually think is the hero of the entire solar array. And this poor guy had to spend about 2 months surveying the entire hillside and then carefully marking each one of these locations. You notice there's 3. So, you know, if it was 2, it'd be easy because 2 points make a straight line, but there were 3. So we had to get all 3 of these things lined up to about 1/4 of an inch on this crazy hillside with each one of these things in a different orientation. So he's definitely the hero. So on top of this is this sort of metal structure which holds the solar panels. You can see the light coming through there a little bit. These guys were constructed. They had a giant factory down there on the soccer field where the guys were building the frames and then putting the solar panels on top of them. And then they had this right over in this corner here, they had a 200-foot crane that was absolutely the most spectacular piece of engineering I've ever seen on campus. And that crane would then lift the panels from the soccer field up and put them into place here. Okay. So that was very exciting. I did not get to ride up in the crane, but the campus photographer took some really cool pictures from up there. So here's what the tables actually look like. You can see it's 11 by 2 of these panels. Each one of these panels is a SunPower 230 panel. That's 230 watts per panel. There are 4,971 of these panels on the hillside. And then also down there, I don't know if you can see it, but there's also panels over the parking lot there. And it has just been a terrible summer. We've had smoke, we've had fires, we had the normal amount of dust, and these things are just horrible. Let's see if I can sort. Okay, so that's what they should look like, and you can see how dirty they are. Because you guys didn't come back to campus, not blaming you, but because we didn't have enough revenue on campus, the college decided not to clean the panels this summer, so they're looking particularly dirty. I think we're probably missing about 30% of the energy we could have gotten. Okay, so then quickly, I know I'm running out of time here. So each panel has a little wire. Those wires hysterically get collected in this trough, which runs all the way down the hill. And then that gets put into a combiner box. That's that little gray thing there. And then the combiner box sends bigger cables over to that metal cage with tan boxes inside of them. So the solar arrays produce DC power. Now, I didn't realize we were doing floor prizes. I'm sort of pissed off about that, but I will offer a floor prize to anybody who can tell me what kind of electricity we use at home. Not DC electric power. Anybody?
There's a comment in the chat.
Oh, and what does the comment say?
AC.
Oh, good job. Okay. So I will download yesterday's data and send it to you as my prize. That's all I got. Okay. So we need to convert DC power to AC power, and that's what those boxes down those do. They're the inverters, and they convert DC power to AC power, which we can then put on the grid and use just like normal power. Okay, that's all I got from up on the roof.
Thank you, Dan. I think it's fair to say Dan said the surveyor was the hero, but the truth is this is Dan's baby. We never would have the solar array without Dan. He is, as President Veach once referred to him, as indefatigable. And I think that that's a fair assessment. This is Dan's solar array. We just give it Oxy's name for propriety's sake.
Thank you, Alex. Not true, but thank you.
Okay, so I want to take a few minutes and I want to talk about the 3-2 program because I know a lot of people have a lot of questions about that. I'm what's officially known as the liaison officer for Oxy for the 3-2 program at Caltech and Columbia. There's nothing formal anyone has to do to get started in the program. You merely have to take the appropriate coursework. So typically what happens is you take the appropriate coursework for 3 years while you're here. You have to maintain a high GPA. You have to have at least a 3.5, both overall and separately in math science. You have to take the courses that Columbia and Caltech insist that you take, they refer to as prereq. And you have to finish all of Oxy's requirements for graduation in the 3 years that you're here, with one notable exception. And that is the one Oxy requirement you don't need to fulfill is the completion of a major in those 3 years. And that includes comps. And the reason is if you end up going on the 3-2 program, you then spend, after your 3 years here, you spend 2 years at either Caltech or Columbia. And it's the completion of those 2 years that Oxy views as tantamount to a major. And so that's why you don't get a degree from Oxy until you finish the 5 years, because Oxy will have said you haven't finished a major. At the end of the 5 years, you get 2 bachelor's degrees, one from us and one from Caltech or Columbia. I think typically we send 2 to 5 students every year, mostly to Columbia. They're not as hard-nosed as Caltech is. Caltech, I can tell you from experience that if you have a single B, even if it's in history, there's a very good chance they won't take you. That's just the way it is. The big change, though, that I want to make sure people know, and I know it's been updated appropriately on the website, but it's really very important, and that is this year's juniors are the last students for whom Columbia guarantees admission. So if you have the GPA and the coursework, then they guarantee you admission. That's part of the agreement that Oxy has with them. In fact, it's the agreement all the schools have with Columbia for the 3-2 program. Starting with this year's sophomores, though, they no longer guarantee admission. And it's not because of Oxy. They're doing this with all their schools. And the reason is quite simple. They've guaranteed admission, and all of a sudden they have more students than they can handle. And so they decided they had to do away with that. Now, what that means is the question everybody always asks me is, what are my chances of getting in? And I'm sorry to say, I don't know. I have no data. Next year will be the first year that I can start finding out. I would like to think, since our students have all done well and finished on time at Columbia, I would like to think that they know us. They appreciate the preparation that we give to our students, and that if you meet the criteria from before, which is to say 3.5, taking all the appropriate coursework, I'd like to think you would be a shoo-in, but I can't guarantee that at all. That's the problem. So the general advice, and it's the same advice we've always had, it's just more important now, and that is to make sure in your 3rd year you're taking coursework so that if for whatever reason you choose to stay at Oxy for a 4th year, you can easily graduate in 4 years. And if you don't do 3-2, it doesn't mean you can't be an engineer. I would say more students do what we call a 4-2 scenario. It's not really a program. Sometimes people call it that. But it's really a scenario in which you finish 4 years at Oxy, most often as a physics major, but every so often as a computer science major and less often as a chem major. And then with your 4-year degree, let's say in physics, you apply wherever you wish around the country for a 2 years master's in your chosen area of engineering. If you look, you'll see that typically masters in engineering are 1-year affairs, but they're presuming that you have an undergraduate degree in engineering. And since you'll have an undergraduate degree instead in physics, then there are courses you have to make up, and so it turns into a 2-year program. But at the end of 6 years, you'll then have a master's degree. If you did the 3-2 program, then after 5 years, you'll have 2 bachelors, and then you could go for a 1-year master's, and at the end of 6 years, you'll have a master's degree. So it's really important to appreciate that 3-2 is not the only way to do it. It's prestigious. There's a lot to be said for it. But if for whatever reason you don't want to, either because you don't want to, you know, work that hard for 3 years and maintain a GPA, obviously a high GPA is always good, but there's more flexibility if you do a 4-2. We had a student many years ago who I'm absolutely convinced would have ended up at Caltech had she actually applied, but she decided that she wanted to stay her 4th year. And I'm pretty sure she told me it's because she always wanted to take French Lit and she knew this was the only chance she'd have to do it. And then she went off to do a 4-2 program at Stanford. So she landed on her feet. It was perfectly fine. There's all kinds of reasons people choose 4-2 over 3-2. But I want people to be aware of how it works. As I said before, there's nothing formal anybody really needs to do until we get to about November, December of junior year. At that point, we need to start working on applications. You can apply to either school or both schools. It doesn't matter, although their timelines are different, and that's always a headache, but we deal with it. And in a nutshell, that's the 3-2 program, okay? I had thought that maybe I would talk a little bit about a combination, if you will, of relativity and quantum mechanics, just to put some physics here. But we're kind of short on time. So if anybody wants to hang out, I'm more than happy to talk about some combination when you put relativity and quantum mechanics together. I think it's better for us to use our remaining time right now. If anybody has any questions about anything, please feel free to speak up. We're all here for at least another 10 minutes or so. Questions about the program, about 3-2, about physics, about research, about VR headsets, whatever. No? Okay. Okay. Well, should I talk for a couple of minutes about relativity and quantum mechanics? Would that be interesting to you guys? Would that be something to do? All right, let's see. I didn't really plan this out, so we're doing this off the top of my head. Let's just state that up front. Okay, where's my screen? It's not coming up. Can you see my iPad? Can you guys see the iPad?
Not yet, Alec.
Nope.
Yeah.
No, it's a blank screen.
Okay, it's not up now?
Nope, blank
Still
screen.
loading.
Oh, it's very strange because I used it this morning. Let's see. There we go. How's that? Better?
We see a big screen now. Yep.
Yeah, okay. Can you see that?
Yep.
Okay. So here's what I want to talk about. The question is, I want to talk about what it means. I want to talk about a fancy word, causality. Causality is a fancy word that basically means that if you have an effect, the cause of that effect has to come first. Okay? So if I clap my hands and you hear me a second later, that's called a causal relationship because I clapped, I sent a signal to you, and you heard it a moment later. But if you heard it before I clapped, that is acausal. There's no way there can be a connection between those two things, okay? So if you do things in relativity, so if I plot, say, distance over here, and typically in relativity, we plot time up here. And then we usually put the speed of light here so that the y-axis also has units of distance. Then this line here is called a light line. And that represents anything that's moving at the speed of light. If you are just standing still, then you're right here and you will move up because you're always moving in time. And because that slope is infinite, that means you're moving at 0 speed because time is up here and space is over here. Okay? So the deal is, so anything that's causal has to be a relationship between a point up here in this forward area here. I can clap my hands here, and you'd be able to hear it here because it requires a speed less than that of light. You guys, I cannot see everybody's face, so I don't know if you're looking mystified or not, okay? On the other hand, a point here there is no way to have a causal connection because it would require a signal from here to here to move faster than light. So in relativity, a causal connection requires that the cause and the effect be within what's called the forward light cone. So this is, you imagine if you put the y-axis here, you can imagine a cone. If you're in this forward light cone, they could be causal. Now, it may not be, it could be coincidence. But if the two things are here and here, they absolutely are acausal. Okay, there's no way. Now, one of the remarkable things about relativity, I'm going to draw this again. If I draw my light cone like this, if I have an event, something A and something B, because A and B are causally related, no matter who views it, any frame of reference will always see A precede B. Okay? A will always come before B. Okay? Got to be able to spell. On the other hand, if there's a C here, these are acausal. There is no way that A could have caused C. And what that means is some observers, there we go, see A and then B, and some see B and then A. In other words, the order of events is not fixed, which makes sense, because if it's not causal, then they have nothing to do with each other. And it's possible that one person will see A before, oh, I'm sorry. Nobody's speaking up when I make a mistake. So what that means is that it is possible that one observer will see A before C, but it's possible another one will see C before A, which makes sense because they're not causally related. But in this case, everybody agrees that A comes before B. Great, that's it. There's your relativity, no big deal. The problem is quantum mechanics doesn't like this. And the reason quantum mechanics doesn't like this is because the light cone is a fixed limit where you say X is equal to C times T. This is a fixed limit. I cannot go any faster than C. But that means if I know where I am, it's possible because of Heisenberg to actually be going a little bit faster. So Heisenberg insists, because of the inherent uncertainty between position and velocity, or position and momentum, there is no way to observe a strict limit on the cone. It's not possible. It has to be possible for some causal relationship between A and C to occur. Now, the probability is outrageously small because all of quantum mechanics is governed by Planck's constant, h bar, which is on the order of 10 to the minus 34 joule seconds. So we're talking about a tiny effect, but it's a big deal because it means that some people could see A before C and other people could see C before A, and it doesn't make any sense to have a causal relation. So imagine, for instance, if you had a proton coming in and it could basically eject what's called a pion, and then a neutron will come out, okay? Perfectly, and then what could happen, this pion could hit a neutron and come in as a proton, okay? So time is this way. And what this will look like to an observer is the proton spit out a pion. The pion was absorbed by the neutron and it turned into a proton. This is called PN scattering. The problem is because of Heisenberg and the light cone not being sacrosanct anymore, it's possible somebody could see it like this. In other words, they will see the pion absorbed before it was ever emitted. There's a technical term for that. Crazy. But that's what Heisenberg does. Now, if it weren't for quantum mechanics, you'd say it's not possible because the light cone is sacrosanct. But Heisenberg says it's not, it is possible. So what the heck is going on? Well, I'm about to give you something that's not exactly historical, but it's close enough. And that is one of the things that Feynman, Richard Feynman, is known for, is he worked some of this out, and he discovered that the mathematics describing this, that this pion going this way is a pion with negative energy, negative momentum, and moving, here's the key, backwards in time. That's what the math tells you, and this applies. Well, what the heck does it mean? You just work out the mathematics straightforwardly, and you end up this pion moving backwards in time. Well, now let's think about it. What does an observer only sees things moving forwards in time. So what is the observer going to see? Well, if this guy over here sees positive charge going from left to right, so this side becomes more negative, relatively speaking, and this guy becomes more positive, then if this thing is going backwards in time, then he still has to see this becoming more negative and this guy becoming more positive. What this ends up being, we can talk about this in more detail. This is taking longer than I expected. That's always the case. People who've been in my class know that. What this is it's essentially a prediction that the only way to make sense of this is that there must exist a particle with the same mass as the pi, but with opposite charge. That is to say, this observer is not going to see a pi plus coming backwards in time. This observer instead is going to see a pi minus moving forward in time. And that's the only way, it's the absolutely only known way to get around this problem. That there must be what we now call antimatter. Antimatter, by this theoretical description, is required to exist in order for causality to make sense. And we'd like to think that the world is a causal place. Causality has to be. And the only way to make it work is if there is such a thing as antimatter, and sure enough there is. There's a pi plus, there's a pi minus, there's a proton, there's an antiproton, there's an electron, there's an anti-electron called a positron. The existence of antimatter is understood to be required in order to maintain causality, that we live in a causal universe. We could talk about this a lot more at some point. This was just trying to get some fun, geeky, cool stuff out there. There's an incredible amount of math that goes in here. We can talk about it at some point, but not right now. Anybody have any questions? Okay. Well, with that then, I guess we're done with our open house. I thank everybody for coming and everybody who participated. Don't hesitate to contact any of us if you have questions, comments, criticism. We're all ears and we're here for you, even if we're not physically in the same room. Don't let that stop you. We're still here and we're still on the job. Okay? So it was a pleasure seeing you all. This will be posted. This has been recorded. And so at some point in the next day or so, it will be posted so you can tell people who may have missed it that it's there. And as I say, please feel free to contact any of us. Okay? Okay, have a great rest of your day, everyone. Hope to see you in class.